Hello, Ziyad.
Good afternoon, sir.
Good afternoon. How are you?
Fine, sir.
So, in the last class, we have finished the moving charges and magnetism.
Sir?
In the last class, we have finished.
Sir? So can you hear me?
Yes,
Sir, can you explain the last question that we did, sir?
actually, last question. This question, na?
No, sir.
This one.
Yes, sir.
So, see here, we are saying a galvanometer coil has a resistance of 15 ohm.
Yes, sir.
A galvanometer coil. I have told you, na, in a galvanometer there is a rectangular coil having n number
Yes.
of turns. Okay,
Yes.
so
Yeah.
that is the interior of the galvanometer.
Yes.
Okay, so a galvanometer coil has a resistance of 15 ohm. Means G is given. I have told you what is G. I have told you G is the resistance of galvanometer, capital G.
Yes, sir.
Okay, and they are saying and shows full scale deflection for 4 milliampere current. Full scale deflection means for the full scale deflection of the pointer. For the full scale deflection of the, I have told you there is a pointer also in the galvanometer.
Yes, sir.
When this pointer deflects full, means this pointer deflects full when the current flowing in the galvanometer is 4 milliampere.
Yes.
Okay, and after that, how will you convert the galvanometer into ammeter of range 0 to 6 ampere? I have told you the conversion of galvanometer into ammeter and voltmeter.
Yes, sir.
So I have told you when you will convert the galvanometer into ammeter, you will connect a shunt in parallel with the galvanometer.
Yes.
Told you or not?
Yes, sir.
So this thing is the ammeter.
Yes,
This
sir.
whole thing is an ammeter, and this ammeter has a capacity to measure the 6 ampere current. Range means the range means suppose the range of the galvanometer ammeter is 0 to 5 ampere, means up to 5 ampere current the ammeter can measure. So
Yes, sir.
I have told you range is written with capital I. So capital I is given as 6 ampere. So
Yes, sir.
now I have told you either you should do this question with formula or without the formula. Okay, so you have connected a shunt resistance here in parallel. So I have what is the condition for the parallel connection of two resistances? This is a resistance, this is a resistance. Both are connected in parallel. In parallel, we know that the potential difference is same. So potential difference across this galvanometer and across this shunt will be same. So I have written here Ig into G.
Yes, sir.
And this current is the total current that galvanometer will measure. I is the range. Okay.
Okay.
Here I have written the range. So this is the range. This current I is going to the ammeter. Now this is the junction point. This is the junction point, and from the junction point, the current will divide it.
Yes, sir.
Suppose Ig current is going in the galvanometer, then the current will go in this branch will be I minus Ig only.
Yes, sir.
So through this whole wire, the current will be I minus Ig, and through the galvanometer, the current will be Ig. So now potential drop, or you can say voltage across this galvanometer is current into the resistance. Ig into G is equal to,
Yes, sir.
here what is the current? I minus Ig into S.
Yes.
Okay, from here I have just calculated this S. I have put it all the values. We have Ig, we have G, we have I, we have Ig. I have put here and I got done. Or simply you can learn this formula also. This
Okay,
formula.
sir.
Okay.
Yes. Okay, sir.
Either you can solve by directly learning the formula, or you can apply directly the formula, or you can just derive the formula and then put the value and then get the answer.
Okay, sir.
Now it's all clear, na?
Yes.
Okay, so in this chapter, that I am going to start electromagnetic induction, and
Yes, sir.
the natural magnetism we will study after the alternating current. Okay.
Okay, sir.
Yeah. So in this chapter, uh, we will study how the magnetic field, how with the help of magnetic field, the current can be produced.
Yes, sir.
Yeah. But in the last chapter, last chapter means magnetic field of current, or according to the NCERT, you can say moving charges and magnetism. What we have studied, due to the current, there will be the magnetic field.
Yes.
And in this chapter, we will study due to the magnetic field, there will be the current.
Okay, sir.
Okay. So write down the heading electromagnetic induction.
Okay, sir.
Electromagnetic induction, and see here is a wire in this current I is flowing. And I
Yes.
have told you in the last chapter, due to the current carrying wire, there will be the magnetic field around it.
Yes, sir.
Okay. So I have told you this introduction. We know that the current carrying conductor produces a magnetic field. In the last chapter, I have discussed. In
Yes,
this
sir.
chapter, we will see with the help of magnetic field, we can produce the
Current.
current. So first thing in this chapter is the magnetic flux. You should know what is the magnetic flux. Electric flux, I have told you in the electrostatics. So what is the electric flux? Electric flux is the number of electric field line crossing an area perpendicularly. Number of electric field line crossing an area perpendicularly is the electric flux. So similarly, the magnetic flux, you can say number of magnetic field line crossing an area perpendicularly. Okay, suppose this is the some area. This is some
Yes, sir.
area, and these are the magnetic field line, and these magnetic field line are crossing this area.
Yes,
Okay,
sir.
so here you can, this is four magnetic field lines are crossing. Okay, consider my fingers as the magnetic field line, and these magnetic field lines are perpendicular to this area. And what is the magnetic flux? Number of magnetic field line crossing an area perpendicularly. So here four magnetic field lines crossing this area perpendicularly. Okay, so
Okay.
the magnetic flux will be 4. Unit we will discuss later. What is the unit of the magnetic flux? So magnetic flux, this is the magnetic flux. Here, how many magnetic field lines crossing this area? 2 magnetic field lines.
Two.
So here magnetic flux will be 2.
Two.
And magnetic flux, I will represent it with phi suffix b.
Okay, sir.
So for the magnetic flux, you should know what is the area vector. You know what is area, but
Yes, sir.
I have told you the area vector in the electric flux also. Area vector, first thing is area. Okay, suppose this is your area.
Yes, sir.
This is your area. This is rectangular area having length L and width V. So what is area of rectangle? Length into breadth.
Yes, sir.
But there is one more thing here. This is the area. Now, what is the area vector? So, for the area vector have two things. One thing is the magnitude, another is the direction.
Yes, sir.
Magnitude is this area. Magnitude of the area is length into breadth, LB.
Yes,
Now,
sir.
there is a requirement of direction. For direction, always remember that for the plane area, the direction of the area vector is perpendicular to the plane of the area. Okay, so
Okay,
this
sir.
is your suppose plane area, and this direction of the pen is representing the direction of this area, okay.
Okay,
So
sir.
direction of area is perpendicular to the plane of the area. So this a cap vector is known as the unit area vector. This represents the direction of the area. This
Okay, sir.
represents the direction of the area. Okay. So how you will write the area vector? First you will write A into a cap. So here a will be your magnitude of area, and a cap is representing the direction,
Direction.
a unit vector in the direction of the area.
Okay.
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 So direction of area vector is outward normal. Okay, outward normal I have told you. This is your area, and this direction of the pen is representing the outward normal. Okay, this
Okay.
pen is normal to the plane of this area. Okay, so now
Okay.
how we will write the magnetic flux mathematically? So magnetic flux is given by v dot a. Okay, what
Yes.
is v? V is the magnetic field. A is the a vector is the area vector.
Area.
Okay,
Yes.
yeah. V vector is the magnetic field vector, A vector is the area vector.
Area.
Okay. So
Okay.
when you will open this, now when you will open this, this will become, when you will open this will become VA cos theta.
Yes.
And what is theta? Theta is the angle between the magnetic field and the area vector. Remember this point. What is the
Okay.
theta? Angle between the magnetic field vector or
And
magnetic
area.
field and the area,
Area.
not area vector.
Yes. Sir.
And remember, area vector is normal or perpendicular to the area.
Perpendicular. Yes, sir.
Theta is the angle between this.
Okay,
So
sir.
this formula you should know. This formula you should know. Now, magnetic flux is a dot product of magnetic field and the area. So you can say magnetic flux is a scalar quantity. Okay. Finally, you will get the answer scalar. So this is magnetic flux is a scalar quantity. SI unit is Tesla meter square. Okay. Why
Okay, sir.
Tesla meter square? Because uh, unit of magnetic field is Tesla and unit of area is meter square. So Tesla meter square is also known as Weber. And CGS unit
Okay, sir.
is Gauss centimeter square. Okay, Gauss
Okay, sir.
centimeter square.
So
And Gauss.
CGS is centimeter, gram, and second, right? CGS. Yeah. Okay.
Centimeter, gram, and second.
And second.
Yeah. Gauss centimeter square is also known as Maxwell, and there is one conversion here. 1 Weber is equal to 10 to the power 8 Maxwell.
Okay.
So first thing you should learn this formula, and you should know what is this theta. Theta
Yeah.
is not the angle between the area and the magnetic field. This is the angle between the area vector and the magnetic field.
Okay, sir.
And here this magnetic field is constant and area is plane. So that is why the formula of the magnetic flux is this V dot A, or when you will
VA
open this
cos
dot product, VA cos theta.
Yes, sir.
So got it?
Yes, sir.
Okay, first take the screenshots, then we will discuss.
Yes, sir. I took this one, sir. Done, sir. Done, sir. Done, sir.
Now, for variable magnetic field or for curved surface area. Curved surface area, I will take the example of sphere. Sphere have the curved surface.
Yes, sir.
Cylinder also have the curved surface.
Yes,
Cylinder
sir.
have the plane surface also and curved surface also.
Yes, sir.
So sphere have only the curved surface.
Yes, sir.
So for the curved surface, your formula will be formula of magnetic flux will be surface integral of B dot dA. Surface integration of B dot dA. So this will be your formula for the magnetic flux when you have a closed surface or curved surface.
Okay, sir.
Okay.
Okay.
So suppose this is your curved surface sphere. This is your sphere. Suppose this is the center of the sphere. So I will take 2 points. First is this,
Okay, sir.
and first is this. We have discussed uh, in the chapter electrostatics how we will decide the direction of area vector for the curved surfaces. So for the curved surfaces, area vector will be like this. At every point, the direction of area vector will change. Okay.
Okay, sir.
Here, this will be the direction of the area vector. This will be the direction of area vector. Now we will discuss the Gauss law in magnetism. We have discussed the Gauss law in electrostatics.
Yes, sir.
So what is the Gauss law in electrostatics? Gauss law is in electrostatics. I have told you, na, electric flux through a closed surface is
Yes.
equal to the charge inside the surface divided by epsilon naught. Okay.
Yes.
So Gauss law in magnetism says that magnetic flux through a closed surface is zero, is always zero.
Yes, sir.
Why? Because see here you have one magnet.
Yes.
This is one magnet and this is the closed surface.
Yes, sir.
So these are the magnetic field lines.
Yes, sir.
See, this magnet is placed inside the closed surface. So from this magnet, magnetic field lines are emerging from the north pole
Yes, sir.
and terminating at the south pole.
South Pole.
Emerging
Yes.
from the north pole and terminating at the south pole.
South Pole.
Now see the flux here, total flux going out of the surface. This magnetic field line is going out of the surface. Now
Yes.
finally this magnetic field line is coming into the surface,
Yes, sir.
and same is the case for this magnetic field line.
Yes, sir.
So basically here why the magnetic flux is zero, because entering flux is equal to the leaving flux. Okay.
Yes.
See here, this is the leaving flux. Two magnetic field lines are leaving from the
Yes, sir.
surface,
Yes.
and two magnetic field lines are entering to the surface.
Yes.
entering flux if you will consider negative, and leaving flux if you will consider positive, then you
Yeah.
can say net flux will be zero.
Yes.
Net flux will be zero. So I am writing here entering flux if you will take positive, leaving flux will take negative, then total flux is equal to, suppose your entering flux is phi 1, your leaving flux is phi 2. So you will write phi 1 minus phi 2, and both the flux are equal because
Yes,
the
sir.
number of field line entering is equal to the number of field line leaving.
Yes,
So
sir.
you will write here phi 1 is equal to phi 2. So total flux will be 0.
Yes.
So you can say here flux leaving is equal to the flux entering. Is it or no? See,
Yes. Yes, sir.
two magnetic field lines are leaving this surface.
Yes, sir.
This is the leaving. Na? These magnetic field lines are leaving, and two magnetic field lines are entering.
Entering. Yes, sir.
So leaving flux is equal to the entering flux.
Yes, sir.
So that is why Gauss law in magnetism is like that. Magnetic flux means number of magnetic field lines. Magnetic flux through a closed surface is always zero because magnetic field line started from the north pole and terminated
At
to
the
the
sub
south pole.
subport.
Take the screenshot.
Done, sir.
Okay. So now you should know what is the dot product of two vector because we will
Yes, sir.
solve the question on magnetic flux.
Yes.
So we should know that dot product
Yes.
because we will have this formula phi is equal to v dot a. So this is the dot product. Okay. So dot product of two vectors.
Yes.
So suppose this is a vector,
Yes.
2 I cap plus 3j cap plus k cap. B vector is equal to 3 I cap plus 5j cap plus 2k cap. So when you
Yes.
will calculate the dot product, you will write A dot B and you will multiply only coefficient of I cap with I cap, J cap
Yes,
with
sir.
J cap and K cap with K cap. So here 2 into 3 is 6 plus
Yes.
3 into
15.
5 is 15 plus 1 into 2 is
21.
equal to 2. That is
Yes.
equal to 21.
21.
So in this way, in electrostatics, we have done this. Okay. So
Yes,
here
sir.
just for your revision.
Okay.
Now we will solve the question. So this is your first question. So here, magnetic field of 2 Tesla exists in space. There is a magnetic field of 2 Tesla in some
Yes,
space,
sir. Yes.
and it is inclined at 30 degree with the plane of the area. And this magnetic field is making an angle of 30 degree with plane of area. With
Yes, sir.
plane of area. Okay.
Yes.
Calculate the magnetic flux through the area. Calculate the magnetic flux through the area.
Very.
So suppose this is your area,
Yes, sir.
this is your area, and this magnetic field is making an angle of 30 degree with plane of area.
Yes, sir.
And I have told you for the planar area, the area vector will be perpendicular.
Yes, sir.
This will be the area vector. Perpendicular.
Yes, sir.
So this whole angle will be 90 degree. What will be the angle between the magnetic field and the area
Theta.
vector?
Theta.
Theta, but
Theta.
what will be the value of theta? See here. This angle,
Yes,
this
sir.
area vector is perpendicular to this area.
Yes, sir.
And this magnetic field is making an angle of 30 degrees. So this angle
Yes,
will
sir.
be 60 degree, na?
Yeah, yes, sir.
Because this total angle is 90 degree.
Total angle, yes.
Why
Sir.
this total angle is 90 degree? I have told you area vector makes an angle of 90 degree or perpendicular to the surface of the
Perpendicular.
area. So
Yes,
that is
sir.
why theta is equal to 60 degree, not 30 degree.
Yes, sir. Okay. Yes.
Okay.
Okay, sir.
So you have area of 10 meter square. Okay, area of 10 meter square and magnetic field of 2 Tesla. You can apply the formula of magnetic flux VA cos theta.
Yes, sir.
So magnetic field is 2, area is 10, cos theta means cos 60.
Yes.
So this will become 20 into 1 by 2. This will become 10 V1.
Okay, sir.
Now next question. So here magnetic field is given. Magnetic field of 10I means this magnetic field is given in the vector
Yes, sir.
form.
Yes, sir.
And exists in space. This magnetic field is existing in some space
Yes, sir.
of area 2 meter square. Okay, in YZ plane. Calculate the magnetic flux. So suppose this is your x-axis, y-axis, this is your z-axis, and your area is in YZ plane.
Why is it?
This is your area, and area is 2 meter square. So first we will calculate the area vector. We have area, we will calculate the area vector. Achha, this area is lying in YZ plane. So what will be the direction which is perpendicular to this YZ plane?
Direction, sir?
What is the direction perpendicular to YZ plane? X-axis, na?
Yes, sir.
So along the x-axis, what vector we have? I cap unit vector we have.
Yes, sir.
So you will write area vector as magnitude of area, that is 2, and I cap. I cap is the unit vector perpendicular to this area.
Yes, sir.
And magnetic field vector is given
Yes.
10 I cap plus 3 J cap plus K cap. For calculating the magnetic flux, you will apply V dot dA,
Yeah, cos theta.
V dot A, because area is plane here.
Yes, sir.
So this will be 10 I cap plus 3 J cap plus K cap dot
2i.
2 I cap. So your answer will be 10 into 2 only, equal to 20 V1.
Yes.
because here there is no term of j cap. Okay, so that is why we will multiply this 10 with 2 only.
Yeah, okay.
So now you can note it down.
That's it.
Just
Okay. Done.
so what is the formula for the magnetic flux? Magnetic flux is equal to B dot A, and magnetic flux is also given by BA cos theta.
Cos theta. Yes.
And what is theta? Angle between the
Angle between
area
the-
vector and the magnetic field vector.
Yes.
And this magnetic flux is a scalar quantity. And definition of the magnetic flux means, what is the magnetic flux? Number of magnetic field line crossing an area perpendicularly.
Yes.
Okay.
Okay.
So this magnetic flux concept should be clear. Now we will discuss Faraday's experiments. So there are 3 experiments, and we will discuss here. So this is some coil, and this coil is connected with the galvanometer. This coil is connected with the galvanometer.
Yes, sir.
There is no battery here, so there is no current in this circuit.
Yes, sir.
Here is one magnet. Here is one magnet. So what is happening? This magnet is moving towards this coil. This magnet is moving towards this coil.
Yes.
When this magnet, and you can note one thing here, due to this magnet, there will be the magnetic field around it.
Yes, sir.
And this coil is in the magnetic field of this magnet.
Yes, sir.
So you can say that due to this magnet here, initially now the magnet is here.
Yes, sir.
Okay, so there will be some magnetic field here due to this magnet.
Yes, sir.
Okay. So how there will be the magnetic field lines like this. Okay, there will be the magnetic field lines from the magnet. So we can say that this coil have some magnetic field due to this magnet. And what will happen when this magnet will move towards the coil? Magnetic field at this coil will increase or decrease? When the magnet is moving towards this coil.
Decrease, sir.
No, this magnet is moving towards the coil.
Okay, yeah, increasing.
Increase, na?
Yes, sir.
Because magnet is going near to the coil.
Yes, sir.
So that is why the magnetic field is increasing.
Yes, sir.
So due to the motion of the magnet towards the coil, the magnetic field at this coil is increasing.
Yes, sir.
And we know that the magnetic flux is equal to VA cos theta, and area and cos theta if remain constant, then you can say your magnetic flux is directly proportional to magnetic field.
Yes, sir.
So what can you say about the magnetic flux when this magnet is moving towards the coil? Here the magnetic field is increasing.
Yes, sir.
Magnetic field will increase, so magnetic flux will also increase.
Yes, sir.
So, okay. So what he had noted that there will be some current in this coil due to the motion of this magnet. There will be some current, means there is some deflection in the galvanometer.
Yes, sir.
There is some deflection in the galvanometer due to the motion of the magnet. So why this is happening? Because when this magnet is moving towards the coil, magnetic field is increasing at this coil. due to the increase in magnetic field, magnetic flux is increasing. And when there is an increase in the magnetic flux, there will be the induced EMF. There will be the induced
Yes, sir.
EMF in this circuit. And due to that induced EMF, there will be some current in this circuit, and that current is known as the induced current.
Okay, sir.
Now, if someone is asking when this magnet is moving towards the coil, why there is the current in the coil, and why there is current in the coil? So, what will you say? You will say that due to the motion of the magnet, the
Yes, sir.
magnetic flux is increasing at the coil. So, due to the increase in magnetic flux, there will be induced current or induced EMF.
Yes, sir.
You can write here. Due to motion of magnet, the magnetic field at coil will change and due to change in magnetic field, there will be change in magnetic flux. Linked with coil and EMF is induced in coil. Due to that, there will be induced current in the circuit. There will be induced current in the circuit.
Circuit.
So this is the first experiment. Okay. Due to the
Okay, sir.
motion of the magnet, the magnetic field is changing at this coil, and due to change in magnetic field, there is change in the magnetic flux,
Yes, sir.
and due to the change in the magnetic flux, there will be induced EMF in this circuit,
Induced.
and there will be some induced current.
Yes.
And this galvanometer is detecting this induced current. Okay, now this experiment, second experiment. Instead of magnet, earlier we have the magnet, moving magnet. Now we have this system.
Yes, sir.
This system is having a coil. This C2 is representing some coil, and this coil is connected with some battery, so there will be some current in this coil. And now this whole coil is moving towards this coil.
Yes, sir.
So we know that the current carrying coil will behave as magnet.
Yes, sir.
There is some current in this coil, so we can say this will behave as a magnet. Due to this system, there will be some magnetic field at the C1, and when this will move towards the coil, what will happen? Magnetic field here will increase or decrease due to this. See, this coil,
Yes, sir.
whole system is moving towards this
Yeah,
coil
increasing.
C1. Increase,
It
na?
will increase. Increase.
Yeah,
Yes, sir.
it will increase. Okay, and when this system When this coil is moving away from
It
this
will
coil,
decrease.
it
It will
will
decrease.
decrease. Okay, very good. Will decrease. So now you can say this system is moving towards this coil. Here magnetic field is changing, na?
Yes, sir.
Increasing means changing.
Yes, sir.
So due to change in the magnetic field, there will be change in the magnetic flux, because magnetic flux is directly proportional to magnetic field.
Yes, sir.
So this magnetic field is due to coil C2. Here also you can write this magnetic field is
Due to coil C2.
due to magnet here.
Yes, sir.
So magnetic field will change, magnetic flux will change. Change in magnetic flux will induce the EMF in this circuit,
Yes, sir. Yes,
and
sir.
due to the induced EMF, there will be the induced current. Okay, so here
Okay.
there will be a deflection in the galvanometer. What is I? Small I is representing induced current.
Induced current. Yes.
Now this is the explanation. Now there is one more experiment. In this experiment, there is one coil, and this coil is attached with the galvanometer, and there is another coil. This coil is attached with the battery, and there is one key. This time this key is open. This
Yes, sir.
time this key is open means there is no current in this coil number C2. So when you will close this coil, when you will close this switch,
Yes, sir.
so there will be some deflection in the galvanometer here. Why? Can you tell me the reason?
Because of the electric fields.
Electric field. Electric field or magnetic field?
Magnetic field, sorry.
Actually,
The
what will
magnet,
happen now? What will happen? See,
the current will pass through, right? If we put the key on, if we switch the key on.
when you will suppose initially this switch was opened.
Yes, sir.
Now suddenly you have closed this switch. So what will happen? There will
The circuit will
be,
get completed, sir.
yeah, the circle will get completed, and the current starts increasing in this circuit.
Yes, sir.
Is it or not? Current
Yes,
will
sir.
start increasing from zero to some value.
Yes, sir.
Okay, now when the current will increase in this coil, so I have told you a current carrying coil behaves as a magnet, and due to the current carrying coil, there will be the magnetic field. Na?
Yes, sir.
So as the current increasing in this coil, there will be the increase in the magnetic field due to this coil.
Yes, sir.
Okay. And the effect of the magnetic field due to this coil will be here also. Means you can say the magnetic field due to this coil will be here also.
Yes, sir.
Because magnetic field is like that. You have, this is a magnet. Okay,
Yes,
this
sir.
is a magnet, and suppose here is magnet instead of this. Okay. So due to this magnet, there will be some magnetic field here, na?
Yes, sir.
Okay. So this coil this time is behaving as a magnet. Here, what is happening? The current is increasing. When
Yes,
you
sir.
just when you just closes this key, the magnetic field is increasing at
Increasing.
C2, and the no, not magnetic field, current is increasing at this coil C2. Due to the increase in current, there will be increase in magnetic field at this.
Yes, sir.
Why? Because there is some magnetic field here due to this coil.
Yes, sir.
So when current in this coil will increase, there will be increase in the magnetic field at coil C1, and we know that the magnetic flux is directly proportional to magnetic field.
Yes, sir.
So this is the magnetic field due to coil number C2. So current will increase, magnetic field here will increase, here the magnetic field will increase. Why it is happening? Because current is increasing here.
Increasing. Yes, sir.
Actually, the magnetic field due to this coil is increasing, and due
Yes,
to
sir.
this coil there is some magnetic field here also. So
Yes,
when
sir.
current is increasing, here magnetic field increasing, magnetic field is increasing means magnetic flux is increasing. When there is a increase or decrease in the magnetic flux, there will be some uh, induced current here, and this galvanometer shows the deflection.
Yes, sir.
Okay, I have
Okay.
written the explanation here. Just read it once. Hmm. As soon as the key is closed, this key is closed,
Yes, sir.
current start increasing in coil C2. So in coil C2, the current will start increasing,
Yes, sir.
and due to which the magnetic field start increasing. Obviously, the current magnetic field is directly proportional to the current.
Yes, sir.
Okay, so you can write here your magnetic field is directly proportional to the current. Current will increase, the magnetic field will increase, and the flux linked with C1 will become 0 to a constant value. Actually, I have to change it.
Yes, sir.
Hmm. Hmm. So magnetic field start increasing, and due to which magnetic flux will increase linked with coil C1
C1.
and EMF induced in C1 and induced current. So there will be the induced current here. Now what
Yes,
will
sir.
happen after some time? After some time, when you have closes this key, closes this switch, after some time the current will become constant. Means this current will not change. This current will achieve some constant value.
Yes,
So
sir.
there is no change in the current. So there is no change in the magnetic field due to this coil C2.
Yes.
So there will be no change in the magnetic flux linked with this coil C1, and there will be no induced EMF. There will be no induced current. Okay.
Okay.
So
Yes.
here you can write after some time the current in coil C2 will become constant. So no change in magnetic field, no change in magnetic flux linked with coil C1. Hence, there will be no induced EMF and induced current. Okay. So Now you can take the screenshots.
Done. Done. Done.
So actually, from these three experiments, what we get? We get to know that we got that when there will be a change in the magnetic flux, when there will be a change in the magnetic flux linked with coil, then there will be induced EMF in that coil.
Yes.
So Faraday has done these three experiments. First, this and after that he concluded that whenever there is a change in the magnetic flux linked with the coil, there will be the induced EMF in the coil. Okay, and that induced EMF is directly proportional to the change in the rate of change of magnetic flux. So that is the Faraday's law. Our next topic, Faraday's law of EMI, electromagnetic induction.
Practice.
So what is the Faraday's law of electromagnetic induction? So whenever there is whenever magnetic flux linked with the coil change, an EMF is induced in the coil, and this induced EMF is proportional to rate of change of magnetic flux linked with coil. Just a minute, Ziyad. So whenever magnetic flux linked with the coil change, an EMF is induced in the coil, and this induced EMF is proportional to the rate of change of magnetic flux linked with the coil. So before that, see this.
Yes.
Suppose at some time t1, your magnet is here.
Yes.
This is your magnet. At some time t1, your magnet is here, and due to this magnet, there will be the magnetic flux linked with coil C1 here also.
Yes.
Here is the magnet now. At some time t1, there will be some magnetic field also. There will be some magnetic field due to this magnet here.
Yes, sir.
Okay. Due to that magnetic field, there will be some magnetic flux.
Yes, sir.
Okay. So you can say phi1 is the magnetic flux at time t1. Okay. Linked with this coil C1. So what is phi 1?
BA cos theta.
Yeah. Magnetic flux linked with coil C1 at time t1. Finally, this magnet is moving, and finally this magnet is here now.
Yes, sir.
And suppose this is at time t2. So this magnet is here, means here there will be some different magnetic field due to the magnet here.
Yes, sir.
Due to this position of magnet, there will be some different magnetic field here.
Yes, sir.
Due to that different magnetic field, there will be different magnetic flux here.
Yes, sir.
Suppose that magnetic flux at time t2 will be phi 2. Okay. Now, what is the delta t? T2 minus T1. Magnet
Yes, sir.
has moved from here to here.
Yes, sir.
Initially, your magnet is here. Finally,
Yes.
magnet is here. So, what is the change in time? This is your magnet, as your magnet is moving like this.
Yes, sir. So,
change in time is delta t. Change in the magnetic flux will be phi 2 minus phi 1. Okay, this is the change in the magnetic flux.
Yes, sir.
Okay. According to the Faraday law, the induced EMF, in this coil is directly proportional to delta phi by delta t. What is this E? Induced EMF.
Yes, sir.
And when you will remove this proportionality sign, you will get K delta phi by delta t. This K is equal to -1 for all system of units. For all system of units. So put the value of K here. So this will become minus delta phi by delta t. This is your magnetic EMF. So your EMF is given by minus of delta phi by delta t. Delta phi means change in the magnetic flux. Delta t, change in the time.
Yes, sir.
So average EMF induced in the coil. So average, we take average for a finite period of time. So this delta t representing the time interval, finite time interval. Okay. So your average EMF will be minus delta phi by delta t again. Instantaneous EMF induced in the coil will be given minus of d phi by dt. Okay, minus of d phi by dt. D phi means a small change in the magnetic flux divided by a small change in time.
Yes, sir.
So suppose your coil have the resistance R, okay, and this is the induced current.
Yes, sir.
Induced current in the coil. So how you will calculate the induced current? Induced current is equal to V is equal to IR, na?
Yes, sir.
So I is equal to V by R.
Yes, sir.
So current is equal to EMF E divided by the resistance
R.
So this will become minus 1 by R delta phi by delta T, or okay.
Okay, sir.
Or you can write it. This is the average induced EMF. Instantaneous induced current will be d phi by dt. You have put the value of this E here in this formula here, and you will get this. Now charge induced for this coil C1. So current, induced current is given by dq by dt.
Yes, sir.
Current is charge divided by time.
Yes.
So from here you can calculate the charge. dq is equal to I into dt. So put the value of induced current. Induced current is minus 1 by r d phi by dt. Minus 1 by r d phi by dt. And here is one more dt. This dt and dt will be cancelled out. So your charge induced will be minus of d phi divided by r. So this is the charge induced in coil. Charge induced in coil C1. Ziyad, are you getting now?
Yes.
Means actually what is happening now? The basic thing here is change in the magnetic flux.
Yes.
If there will be a change in the magnetic flux, there will be the induced EMF in the coil.
Coil. Yes.
Okay. Yeah. Okay, note down this.
Done. Done. Done.
Done?
Yes.
Okay.
Done.
Okay. So, and note down these 2 points I am explaining. Open circuit means suppose you have opened this circuit from here like
Yes,
this.
and the previous one we did, right? With the switch.
So yeah. So open circuit means there will be current or no current?
No current.
No current. So in open circuit, induced EMF exists, but induced current is zero.
Yes.
But in closed circuit, there will be both induced EMF and induced. Take the induced current also. So just
Yes,
take the
sir.
screenshot of this.
Done. Sir.
Okay, yeah. So I think that's all for today. And I have what I have told you in the last class. So I will take your Viva today of the last chapter. Okay.
Yeah.
Okay, no problem. Now, just a minute. So here we will discuss. So from the last chapter, uh, that is moving charges and magnetism. Tell me what is magnetic field?
Magnetic field, sir.
I mean the definition of magnetic field. The space around a magnet in which another magnet experiences some force.
Some force. Yes. Sir.
We have discussed now magnetic field here in this chapter here. This is I have written the definition. Space around a magnet where its magnetic properties exist or the strength of magnetic field. I have told you this is the magnet, okay, and this is the space around the magnet. Here another magnet is coming. This magnet is experiencing some magnetic force.
Yes, sir.
Okay, Acha, tell me what is Biot-Savart law?
Bytes over time? The equations, sir, or the
You can tell me the equation only.
dB is inversely proportional to ideal sine theta.
Actually, I have told you the Weier's-Sabot law. There is some current in the wire. Suppose this is the wire.
Yes.
There is some current in this wire. So if you will calculate the magnetic field at this point, so that magnetic field you can calculate of the small element of the wire only. Okay, and that this magnetic field will be directly proportional to
Ideal sine.
ideal sine theta and inversely proportional to r
Um,
square. What is
R
r?
square.
This
R
will
is
be your
the
r, and this is your theta.
yes, sir.
Okay, okay. So just tell me, suppose this is the magnetic field here.
Yes, sir.
Magnetic field is along x-axis, suppose,
Yes.
and this magnetic field is v vector, and from here a charge q is moving with a velocity v in this magnetic field.
Yes, sir.
This is making an angle theta with the magnetic field. What will be the magnetic force on this charge?
Magnetic force on Q.
Sorry, I have told you now the Lorentz magnetic force. Let's see here. This is a charge moving with some velocity. This is the magnetic field. What is the formula of the force? Q V cross B is given by Q V V sin theta. Okay.
Okay.
Okay. Suppose there is one magnetic field along x-axis, and in this magnetic field there is wire of length L and area of cross section is A, and current in the wire is capital I, and this wire is making an angle theta. This wire is making an angle theta with the magnetic field. So what will be the force on the wire? What is the formula of the force on this wire? So you can
So you
try
can
if you.
repeat the entire
I'm
thing, sir,
just.
the statements.
I'm saying that there is one magnetic. There is magnetic field.
Yes, sir.
In magnetic field there is one wire.
Yes.
That wire carries the current I and having the length L. What is the force on the wire? I have derived now. Force on a current carrying wire in magnetic field. See here. This is the wire.
So
This is the magnetic field.
So Q will be
No. QVB is different. You have this. Force on the wire is given by I L V sin theta.
oh,
In vector form, you can write I L vector cross
V vector.
V vector. Okay. So last question. So tell me, uh, suppose this is the magnetic field along x-axis, and a charged particle is moving perpendicular to this magnetic field.
Yes.
Charged particle is moving perpendicular to this magnetic field. What will be the path of the charged particle? Here is the magnetic field.
Yes.
This charged particle moving perpendicular to the magnetic field. So what is the condition when the charged particle moves perpendicular to magnetic field? It will follow a circular path. Okay, it will follow a circular path. I have told
So
you
the
now.
you're talking about the charge, right?
Yeah, I am talking about charge. So that follow the circular path, and
Yes.
the radius of that circular path is given by mb by qb. We have
Yeah.
discussed
Yes.
this here. I think I have discussed path of the charge when the charge particle is moving parallel, when the charge particle is moving perpendicular. Okay, so this is the circular path.
Yes, sir.
Okay, yeah. So yeah, you can just revise your notes. Okay, and
Yes.
if you have any doubts regarding the previous chapter, and आपको क्या करना है साथ के साथ रिवाइज करना है. Okay,
Yes, sir.
you have to revise along with the chapter that you
Yes,
are
sir.
studying, and if you have any doubt regarding